Okay, good afternoon, everybody. Right.
Gases.
All right, so today we're going to continue with our study on waves. Last class we saw um, the wave equation, how to calculate the velocity and how to calculate velocity, wavelength, and frequency of waves. So today we're going to talk a little bit more about frequency, wavefronts, and we would see some examples. So frequency. Right, so we didn't speak about a frequency of a light because we know light is a wave. Right, so the frequency of a light wave determines its color. Now, as we will come to see shortly, well, not shortly, but probably in the next class, it has an electromagnetic spectrum. Right, so that means it has way more light than what we can actually see or perceive. Okay, so we would see that when we come to it, but we would just take this for granted for now because we know that light is a wave, so we want to be able to determine what color we are seeing. Right, so red has the lowest frequency and violet has the highest frequency. Okay. Of course, this is of the visible spectrum. All right, so I should probably put in brackets here, visible spectrum. That is the light we can see. I believe in the last class, we saw that radio waves also travels at the speed of light. So radio waves are light waves. Okay, so when we come to that, we'll see it. So we want to discuss what a wavefront is now. Can anybody define what a wavefront is for me?
A perpendicular line on a wave that is in phase.
Yeah, so it's just, this is the line or a line. So a wavefront. Right, is a perpendicular line right to the propagation of a wave propagation of a wave um, on which all the points are in phase, right? On which all the points are in phase. Right, now what does this mean? Right, well, firstly, we generally take wavefronts to be either taken to be the crests of transverse waves, right, and the compressions of longitudinal waves. So if you were to draw what these wavefronts are, so let's say I have a wave like this, and I have a wave like this. Right, these are the same wave, well, more or less. So my wavefront would be this one. Remember, the crest is the one on the top, so let's just define that again. Right, so this point is called the crest, and this point here is called the trough. right? It's called the trough. So we take it for crest. So if I was to continue this wave, right, the next wavefront would be right here, right? So these are wavefronts. All right, and for the longitudinal wave, so this is the transverse one, and for the longitudinal one is where we take the compressions, right? So the compressions, remember when we was doing the longitudinal wave, we have like a series of points, and then we have the rear refraction, then we have some compressions again, and rear refractions, and so on. So these here would be the wavefronts, these points, since they are the compressions. Okay, so that is essentially what the wavefront is. Right, it's just the it's an easy way to show the well, the crests of a wave. Okay, now why would that help us? So let's go here and define speed. Let's define speed. So speed v, right? So speed v, so this is what we put speed as. This is the rate at which the wavefronts of a wave propagates. So this is the rate at which the wavefront propagates. Now, and well, of course, it depends on the medium of propagation, right? Full stop. So the rate at which the wavefronts propagate is not just the frequency, and the distance between the two wavefronts is a wavelength. So we can define speed as we saw previously with frequency and wavelength, right? And of course, we know that light slows down in a glass, or as as um let's look at two cases. So we have when things are being reflected and when things are being refracted, right? So reflected means that it's just bouncing back, or if you want to call it that. So let's take a look at two cases, because we really have two cases to really consider here. Well, at this point in time, right? So we have our plane source. This is what is emitting our waves, and this is our barrier. Right now, the barrier could have been perpendicular as well, or parallel, but it really doesn't matter. So the waves will come in like this. Right now, these are wave fronts. Right, until now it would reflect like this. Right, but in this reflection, the speed that it is coming in is the speed that it is reflected out of. So speed are the same. Speed is the same when reflected. Right. However, in a denser medium, So in the other case, we have a plane source and we have our denser medium here. Right? So we have our denser medium. Our wave will be coming in. And the more it goes in, the more it bends. Right? So we would see until it all comes in. And we would see that the wave has to travel a longer distance rather than a straight line. Or you could say that the speed of the wave. So if we call this outside here x and this inside here y, where y is the denser medium, the speed of the wave in x is faster than the speed in y. All right, okay, let's write the x speed is bigger than the y speed. Either way is fine. All right, so I would leave a little bit of homework here for you all, so you'll see the you could go and read up about the variation in the speed of waves. All right, so read on the variation of the speed of waves. So homework. Read on the variation of the speed in waves. All right, and you would actually see that, well, when they get a chance of reading on it, you would see that the sound waves in water actually travels faster than the sound waves in air. Right, and in fact, the sound waves in steel travels faster than the sound waves in air. Right, so you would make sense of that when you read it. Okay, so what I want to do now is talk about the general wave equations again and some properties. And next class, we will look at some examples. Right, some examples, and we should be able to move on to the graphs of waves and sound waves. Right, so the general wave equations. Right, so we have the general wave equations. The general wave equation. So we saw previously that V is equal to F lambda, right? Or you could say V is equal to lambda over T, where T is a period, right? Either one is fine because remember F is just 1 over T, so it's really the same equation. Okay, so we're gonna define something that we would see, but I don't want you to think on it too much. It's just a number, right? We're gonna define the refractive index of a material. This tells us how much more dense something is than the other one, right? So as you would see in the picture, if we did the let's just draw the picture here, right? This is our normal line, and we have an incoming beam like this, and it will bend towards the normal because it's a medium. Right, and we call this here theta 1, and this here theta 2, angle theta 2. Okay. Right, and we on our wavefronts coming in on this line. That this here will also be theta 1. And so on. Right, so this here will also be theta 2. Right, so what we want to define is that the ratios of the velocity, that means out here would be v1 and inside here would be v2. Right, the velocity outside and the velocity inside. And this one here would be the refractive index of the first material, and this would be the refractive index of the second material. So v1 over v2 depends on the wavelength in the first material divided by the wavelength in the second material. And that is also equal to the sine of the angle in the first material over the sine of the angle in the second material. But this is equal to the refractive index in the second material over the refractive index in the first. And this is the equation here. All right. Now this equation actually tells us quite a lot. So we could say what theta 1 and theta 2 is. I will just say it. Right, I wouldn't write it. Theta 1 and theta 2 are the angles of incidence. That is the angle incoming, and the refracted angle of refraction. That is the refracted angle. That is the angle at which the light ray bends towards the normal. The normal meaning the perpendicular line here. Okay. Now the speed of the wave, the wavelength of the wave, and the sign of the wave all change in some proportion, right? But the period and the frequency do not change. They don't ever change. Okay, so if you had red light going in the material, you will get red light coming out. If you had, let's say, green light going in, you'll get green light coming out. It will not change the frequency. What it could change, however, is the speed and the wavelength. So when we come to light waves, you would see that we could actually create a rainbow in the lab using a refractive material. Right, I don't want to spoil it right now. So when using the equations and calculations, it's a good idea to use the relevant letters as subscripts, and that would reduce errors. Like are we using V1 and N1, right? People prefer to use VI, meaning the velocity incident, and VR, meaning the velocity refracted, right? Whichever one you prefer, right? I prefer the numbers because for some reason, right? But some people prefer Ni for the refractive index of the incident material, or which one was in first, and Nr for the refracted material as you want to do the refraction. Whichever one you prefer, you could use, right? Once they remain consistent. And yeah, so that is basically it. Well, this is how far I wanted to reach in the class. But seeing that we have some time, I would like to do this example. A wave has a speed of 3 meters per second, and its crests are 5 meters apart. It approaches a reef at an angle of incidence 60 degrees. On passing over it, the distance between the crests reduces to 4 meters apart. So determine for the wave the frequency in the deeper water. So what we would do for this question, so part A, the frequency in the deeper part. So we are told the velocity of the wave. So the velocity of the wave is 3 meters per second. So we could use V is equal to lambda F, and we could solve for F. So we could get F is equal to V over lambda, and our velocity was 3, and our wavelength, because if we had the distance between crests, right? Sorry, let me just draw this a little better. Right, this point to this point is the distance between the crests, and notice that those 2 points are in phase and they are a wavelength apart. So what they tell us is the wavelength of our wave is 5. Okay, so the wavelength of 5 is 5. So we can say that the frequency is 0.6 hertz, or if you want per second, that's also fine. All right, so part B asks us the period in the deeper water. So the period of the wave is just 1 over the frequency. So part B, the period is equal to 1 over 0.6. All right, so we have that being, let me write the equation first. So 1 over F. So that is equal to 1 over 0.6, which is equal to 1.67 seconds. Okay. All right. Now part C asks us the frequency of the wave as it passes through or passes over the reef, which is the shallow part. Now remember that the frequency of the wave does not change. So C, all right, so is also 0.6 hertz, since the frequency does not change. Doesn't change. Okay. Part D asks us the period as it passes over the reef. Well, if the frequency doesn't change and the period depends on the frequency, D is also 1.67 since, well, seconds, since the period doesn't change as well. Okay, nice. They ask us now, part F, the angle of refraction on reaching the reef. Right, so remember the reef would in a sense be the denser medium. So we have part E would be V1 over V2 is equal to sine theta 1 over sine theta 2. And that is also equal, I think, was lambda 1 over lambda 2. Now we didn't calculate the speed. We didn't calculate the speed of the wave, so I would use this equation here. And what I want is the theta 2, because I want to know that angle. Okay, so how would I work that out? Wait, did I miss something? Part E is the speed, sorry, the speed at which, so probably forgot that one. So the speed at which it is traveling over the wave. So we have V1 again over V2 is equal to lambda 1 over lambda 2. Right, we can use this one because we are given the wavelength in the both scenarios. So the wavelength in the both scenarios, so we have V1, we calculated, well, we didn't calculate, we were given that, so that's 3. So you have 3 over V2, which is what we're trying to find, is equal to lambda 1 was 5 and lambda 2 was 4. All right, cross multiplying, we get 5 V2 is equal to 12, and divided by 5 on both sides, we get V2 is equal to 2.4 meters per second. Okay. All right, so that is the velocity in the shallow part. And as you can see, it is less than the velocity in the deep. Now the angle of refraction on reaching the reef. So the angle of refraction, so that's what we're going to do just now. So that's part F. We have V1 over V2 equals sine theta 1 over sine theta 2, which is equal to lambda 1 over lambda 2. Now, you could have used any one, because now that we know V2, you'll get the same answer. You could use this one, or you could use this one. All right, so since I was going to use the lambda 1s and lambda 2s earlier, I would just use that one. So I have sine theta 1 over sine theta 2 is equal to lambda 1 over lambda 2. All right, so when we come back, we will take a look at. Okay, so we are back. And what are we trying to find? We are trying to find the angle of refraction. We are looking for theta 2. Okay, so we are trying to solve for this angle here. So we are told that sine theta, well, theta 1, it came in at a 60-degree angle. So we have sine 60. Right, make sure your calculator is in degrees, because they give us the angle in degrees. Is sine over sine theta 2 is equal to lambda 1, which was 5, over lambda 2, which is 4. Okay, so we could cross multiply. So we have 5 sine theta 2, sorry, is equal to 4 sine 60. Okay, so sine theta 2 is equal to 4 sine 60 over 5. And can anybody give me that value? 4 sine 60 over 5. I'll take 3 decimal places.
0.693.
0.693. Okay, so we have theta would be, theta 2, I should say, would be sine inverse of 0.693. Give me 2 decimal, at 1 decimal, please.
Yeah, 43.8.
43.8. Okay, so I will take let's say that is 44 degrees. All right, the nearest whole number. We'll take the nearest whole number. All right, so 44 degrees. Okay, and the last part asks us for the refractive which is equal to sine theta 1 over sine theta 2 which is equal to n2 over n1. Now what we want to find is, we want to find this ratio, because they didn't really give us the refractive index of the deep water. So we would just take the ratio. All right, so the easiest one that I see right now is we could use lambda 1 over lambda 2 is equal to n1 over n2. So we'll get lambda 1 over lambda 2 equal to n2 over n1. Right, so we have the n2 over n1. That will be equal to 5 over 4, because the wavelength in the deep was 5, the wavelength in the shallow was 4. And remember, we say that we're using the shallow as as 2 and the deep as 1. So we have n2 over n1 will be 1.25 or 1 1/4. And this have no units. Why doesn't it have units? Because we have wavelength over wavelength, so you have meters over meters, the units cancel. All right, so it have no units here. Right, I probably forgot to put, no, I had no degrees. Let's make sure all my units there. Yes, meters per second. Seconds, please. Right, so another, and this concludes the example. So that is it there for today. Do you all have any questions for me? Feel free to ask it. And if not, I will see you all in the next class.